Hello, everyone. Sorry, I'm a little bit late. Hope you're having a great day at Databricks. So I'm Sharon, and I'll be talking about composing high accuracy AI systems using small language models, SLMs, and mini agents. So devising these smaller agents from either open source models or a set of different model calls. Let's see. So a little bit about me. So I'm Sharon, really good to meet you all. I'm the founder and CEO of a startup called Lamini that builds infrastructure, post-training platform that includes fine-tuning and reinforcement learning to improve often open models, SLMs, and building out mini agents. My background before this was I was computer science faculty at Stanford, leading a research group in generative AI, where I also did my PhD in generative AI with Andrew Ng. I get the great pleasure of teaching millions of people online in generative AI with deep learning AI and Coursera. Before this, I was the product manager at Google, kind of working on Google Cloud with Fei-Fei Li. And it's not announced yet, but actually I am working on something new now. And I'll be sharing a little bit more after, talking about composing AI accuracy, about some thoughts I've been having from that. Like how does, composing AI agents actually help us with AI progress overall? And how does an open ecosystem help us with that? So I'll touch on that at the end if you want to stick around and hear some thoughts, or I'd love also to hear your thoughts. So here's the agenda. I'm going to first talk about high accuracy AI agents, how to compose them, kind of the learnings I've had working with different enterprises about that. Why factual accuracy is really hard. Getting these models to not hallucinate, really, really difficult. So how do we get them to be a little bit deterministic? How do we get them to be a little bit deterministic, inject a little bit of that determinism into a highly probabilistic process? And then, of course, talking about how do we scale these agents and what is necessary in this world for us to be able to scale these further, both for each of our own applications, but also AI at large. All right, so starting with the first part, what you guys came for. So according to Gartner, the stat of a third of enterprise apps will be powered by generative AI and agents. I actually think this is way too low now, but here is the stat. And of course, there's so many different systems out there still. So of course, maybe this is the right target. People often ask me, if we just step back, why do these models hallucinate? Why do they make stuff up? Why do they get so much right and sound so human and yet mess up very simple things like the accurate date that Dave Aguilar climbed the Golden Gate Bridge, which is clearly in its training data because it's on the public Wikipedia page. And the reason is actually fairly simple. It's how it's trained. It's not just the data you feed it, but how it's being trained when you do feed that data to it. And so when I ask a general model, like what year did Dave Aguilar climb the Golden Gate Bridge? And if it starts to output, starts to decode, he climbed it in, and it needs to then sample the next token, a model that hasn't been trained will sample a date-looking thing just as likely as sampling the token for a cat. Okay, that's not great, but it hasn't been trained. It hasn't seen anything yet. So after you've trained it, maybe it'll sample things that look like dates, right? More likely than cat, and sample maybe a little bit less likely, but still more likely than cat, something that looks like a number. Okay, and so it's relying on similarities when it's operating on that date. And similarities are really powerful, okay? So like, even though it might get the date wrong here, the correct date is 1981, but it might sample 1970 because it kind of looks about the same. That similarity is really detrimental in this case, but overall, that similarity is really valuable. It's actually the magic behind these models at all. And just to give you a really simple example, it's kind of like, back in the day with a little bit more like lookup table-y stuff, I would say hi to maybe that bot, and it could interpret hi, but if I said howdy, it would just break, right? So it's like those things are similar, but it doesn't know that similarity. For these models, they actually understand that similarity. Hi, hello, howdy. It can respond and understand how you are engaging with it. That's a really powerful thing that it can handle in that very simple case, and of course that can scale to very difficult, complex cases. But in this case, I want it to be super precise. I don't want it to be sampling from that bell curve. I really, really don't. I really want it to actually be sampling from something that looks more like a Dirac delta distribution on 1981. So only going to sample 1981 in this context and nothing else. Like 1970 should be sampled as likely as the word cat. Okay, that's what I want it to do. This might be obvious to some of you, but why having that factual accuracy is important is because it opens up a new set of use cases. And what I found just working with a bunch of different enterprise customers, talking to thousands of them, is that it's not just about this one use case where, you know, suddenly they can either do or make it more precise that they were already doing. It's actually just the opportunity of opening up a completely new set of use cases that they then have the agency, the ability to then go push forward and make it more precise on their own. And precision is everything for a lot of different agentic use cases. I'm sure many of you have tons of agents running around over a unified agent, and if one of them has an error and it passes it on to another agent, that error compounds. So having that precision early on in your pipeline is extremely valuable. Okay. So that is ultimately the value, is opening up new use cases. In order to get these like factual learning to actually work, though, like when you give it a data point of, hey, Dave Aguilar climbed the Golden Gate Bridge in 1981, if you really want the model to remember that, there are a lot of things you actually have to consider to get it to, but it can, it really can. So the first thing is around data, and we're at Databricks Summit, right? And I spend every time I talk to the folks at Databricks, the co-founders at Databricks, we talk about how important the data is that we give to the model. Garbage in, garbage out. It really is about what kind of data you give it. And so if you give it Dave Aguilar climbed the Golden Gate Bridge in 1981, a million times, you overwhelm the model with it, it's going to know that sentence. But it might not be able to handle that similarity super well anymore, right? So if you ask the question in a slightly different way, it might not really work. So that data is super important. So giving it that appropriate data, being able to see 1981 appropriately, and being able to then have the right algorithm to backprop that into the model so it remembers that is really important as well. So getting your data right is super essential to whatever algorithm you give to the model. And by data, I mean it could be data in your prompt, right? It could be just adding that line a few times in your prompt, far more times in your prompt. It could be fine-tuning the model. It could be adding it to your reward model, right? If you're doing reinforcement learning. So that data is going to show up in a lot of different places, in a lot of different methods as you scale complexity, as you try to get the model to improve with more and more complex methods, if the simple methods don't work out of the box. Okay. But getting the facts right is important. So if you can't get the facts super right, it is going to learn the wrong facts that you want it to learn. The next topic I'm sure you've heard about, because I think people are starting to talk about this a lot, is around evaluation. And I think if we take evaluation to the limit, it basically says that, the AI, where it's going to shine is where it's going to be easily verifiable. So easily evaluated, right? Like that's why we're starting to get good at kind of math problems. That's why coding is so popular with AI. It's because we can actually improve the models quite a bit when we can verify the output. And we can verify it in so many different ways. One for, I actually find this equivalence really interesting. I was talking to some other researchers about it, but essentially in fine tuning, when you're doing like SFT supervised fine tuning, you're doing something actually very similar to the data in order to get, in order to filter it out, just like you do for evaluation. And what you're doing is you're doing rejection sampling. So for all the data that you could possibly have, you want it you want to filter that data to only the high quality set and give the model those positive examples in a similar way, but in almost a softer way, not a hard rejection sampling. And for a reward model, or when you're looking at reinforcement learning and you give a positive, negative reward on an example, you also keep those negative examples. And that also is another way to basically provide that signal back to the model. And I think all of this is connected to evaluation, and evaluation is really key. I think evaluation, the hardest thing that I find when it comes to evals very practically, is just people think it needs to be perfect. And they spend too much time on it, or rather, they think it takes too much time as they try to build it up. and then they realize, oh no, I don't even want to bother doing this. But actually a really good best practice, which I know a lot of machine learning researchers share, is actually just start with a really bad eval first. Just start with one that you think is kind of bad, just so you can get started to see how the model is generally doing. And keep it really small, like something you can handle and just look at and know what the model is doing. So like 20 examples, right? It doesn't have to be anything complex, and something you just put on a page so you can get started, because iterating on something is easier than starting from a blank page. So evals is really critical to improving the model. And I know that foundation model companies spend a lot of time crafting their evals to improve at every single stage of training, from pre-training, which is actually easier because you're usually just looking at loss, to post-training, which is making sure the model is constitutionally, is being safe, is acting safely, is not being sycophantic. I'm sure some of you saw the blog post from OpenAI around that. But yeah, that's super essential. I think another thing just to kind of instill that's really important is around fast iteration cycles. Something I find really interesting that I've observed is, in some ways, machine learning and AI, working with AI, is a highly iterative process, and therefore closer to product design than it is to software engineering. And I find that really interesting because that's almost counterintuitive. You feel like, software engineers, machine learning engineers, we all write code. But actually being able to iterate really fast and have a lot of experiments, or what a designer would call prototypes, is actually extremely beneficial. And it's okay if it's wrong the first time, the second time, the 1,000th time. GPT-4 was rumored to be 20,000 training runs. So just a lot of different runs to see how something is doing. And it's highly experimental. We can't always predict emergent capabilities from these models. So that makes it harder to predict and work with. But what we can do is reach for N experiments. We can say we're going to do 100 experiments within this time frame. And that's usually the way we kind of think through how to measure progress, I would say, across a team. So all of these need to be in place for any kind of learning algorithm to be effective, because your learning algorithm, which is, whether it's fine-tuning, reinforcement learning, or even you just iterating on your prompt, is going to be very good at optimization and optimizing the model for whatever you give it. Okay, so that's all fine and good. Maybe you have a model that's really precise and able to do some of those things. Maybe you got your evals in the right place. It's doing really well on evals, getting that 90% accuracy. But how do you put this together into an agentic system? So this is one such system that we've worked with a big customer, and essentially it's contract review, right? They have tens of thousands of contracts every couple of weeks, and it's just really overwhelming to be able to handle all of those contracts. It's bottlenecked with in-person team looking at very precise language. So how do they get agents to help with each step of the process? I know people probably are really familiar with agents. I'll just define it real quick because I think there's like a million definitions. But essentially, I think of an agent, I really like this analogy from one of our customers. It's kind of like a robot, a program, but it has this brain inside of it, and you can specialize that brain in different ways through tuning the model and adjusting its weights to achieve those specialized tasks better. And it can take those actions, whether it's across the web or using tools locally on your computer, to be able to accomplish that task. And for it to be reliable on facts, you have to make sure that the errors don't compound. And again, that's what I was talking about a little bit earlier, which is, how do we make these models precise so those errors don't actually compound? Okay. So we talked about putting together things into a multi-agent system. We talked about how important data is and I think that's super important at this conference, but not even just at this conference. I think for AI, it really is about the data, and that's what you can control the most. And we'll talk about compute later. But essentially, I think one really big hack that people don't always realize, it's almost like a cheat code, is synthetic data. And I think people are starting to use this more and more, but I think to the limit, what people don't realize is how valuable it really is. If you look at a mature AI application, machine translation, if you go talk to that team at Google, they will tell you that they actually don't use human labeled data anymore. It's actually worse than machine-generated data, right? AI-generated data, synthetic data, as rated by professional human translators. So, and it improves the model significantly more. So in a weird way, it's actually created this flywheel effect where the model is able to improve itself better than any human could. And it's a really powerful force. So I think that's where things will go as things mature. Right now, this is not the case for every application, of course, and a lot of human intervention and adding your taste into it, adding what you know as knowledge, as facts, as important institutional expertise is important to improving these models. But yeah, so what does the process look like? One is you can start with a very small set of examples. So to get started, you don't need to feel like, oh, I have to go, gather thousands or millions of examples. You can start with just a few. And you'll see that that's clearly a theme, like just get started, don't be blocked. And then you can use agents, right, internally to actually generate a lot of that data. From those small examples. And then you can use agents to filter that data and that criteria. You can, again, reuse those filtering, validating agents for your evaluation. But essentially, that's what you can do, that generation and filtering, that validation. And then you can also combine it with deterministic validation. For example, one really common use case that I had been spending a lot of time on was text-to-SQL. So SQL is really special because you can see if it is valid or not, right? You can test a bunch of things. Is it optimized or not? There's so many different features you can actually evaluate from generated or non-generated SQL statement. And that's really valuable because then you can actually give a lot of feedback there. And then you can get that high quality data set. But what's really cool is I actually think, so you can get that data set and you could spend like a god-awful amount of time sifting through that data set, figuring out, is this really the data set to improve my model, or do I need to add more? What do I have to add more? Traditional machine learning headaches. Instead of that, you can actually start to give what I call vibes-based feedback, kind of like from vibe coding, but I believe in a future where we can like vibe tune these models so that they can actually improve from our very casual natural language feedback. But the idea is you can give vibes-based feedback because that just turns into changing the prompts of the generator agents and the validator agents to edit its own training data and improve itself. So I find this flow really compelling in a way where it helps me believe in a future where these models will actually truly self-improve and help themselves. And I think this flow actually already works today. We've had several folks actually implement something like this, and it actually improves the model significantly while reducing a huge amount of developer time. Okay, so this mentioned a little bit around SQL. Kind of what does this actually look like concretely? This is, again, a simple example, but you can look at a schema. So you can look at a pretty complex schema. And we worked with some pretty big customers on this, and it actually generalizes, which is cool. I find that really cool. It's like this whole system or this whole pipeline generalizes to another really complex schema inside of an enterprise. But this was with Colgate, the toothpaste company, so get ready for AI toothpaste. But essentially starting with the schema, and you can just, kind of lay out what the schema looks like and give maybe examples of what the format for each column kind of looks like. And you have an agent that can actually convert that to very simple SQL. And then you can have a pattern question agent that can actually look at the possible questions that a user might ask the system and identify patterns and then generate more from those patterns. And of course, you can take those questions, decompose them further, and then be able to generate more there. And then doing variations, et cetera, and then having a validator agent. This is just here to demonstrate that it can get pretty complex when you're generating all of this data. You can keep getting more and more variations. And the important thing is to cover breadth, so the model has seen kind of the breadth of what you might give it. And what I think is really special is if you do decide to venture beyond prompt engineering and beyond RAG and actually try to fine tune or do reinforcement learning, some kind of post-training technique on your model, you'll get to see that, some kind of interesting generalization whether it's localized or more broader, emerge from these models. I don't know if you guys remember this from a very, very early checkpoint of DALL-E, which is now ChatGPT, I guess, generating images. There was an avocado chair. This model early on was able to generate an avocado chair, having never seen an avocado chair. This is a very magical moment, at least in my life. But it had only seen pictures of chairs, and it had only seen pictures of avocados, and it was able to generate avocado chairs. I know why that's important here is that I think it's really hard for people to somehow take that concept and see it here, but let me just spell it out here. What that means here is that you can have question-answer pairs as your data for just this one column in your column A in your database, maybe doing a join with column or with another table, right? But basically, you can have that just column A, and then you can have another question-answer pair with column B, and then suddenly, and it has the concept of joins, and suddenly, even though you don't have examples of column A to column B, any kind of data point doing that, it's able to generalize to that. That's what's really magical. If you can give it all of that data to learn from. So that's kind of the magic point. Of course, that generalizes to much more complex things, but you don't therefore need to have every possible combination in your data set, because that would just turn into a lookup table. Okay, so maybe just to summarize the value of agentic AI, I'm sure you've seen things kind of like this, but essentially there's that model intelligence layer with reasoning and factuality being really important, scalability and cost effectiveness. So data is really, let me just start with this. Data is really, really important. That is going to be the big differentiator, I think, across different applications. We're gonna have similar optimization methods. Candidly, people are gonna converge on very similar methods there. And of course, I think many of you know, but don't get too invested into one model or framework as new models still do come out, maybe less frantically as in 2023. But yeah, and future-proofing some of those pipelines, such as the one you saw with SQL, like that being able to generalize to another use case or another specific customers is really, really important. Scalability and cost effectiveness is really important too. Kind of the methods I showed here are for when you need the model to really improve its accuracy and really think through how do I eke out more accuracy from this model? And typically you're looking at trying to save costs because you're using a smaller model for maybe the same kind of API call that you're doing with GPT-4 or Claude. And then secure data infrastructure, making sure it's private and secure using open models is a great way of achieving that. And finally, making sure that you are using things that are compatible, right? So using things that are portable across whatever layer of the stack that you're operating on, but things that are portable across the closed model APIs and the open ones. And I think things have really converged that OpenAI SDK at the highest level, and things are converging all the way down the stack, all the way down to the silicon, which I'll share a little bit more later if we have time. So that's about how to compose these AI agents that can work together, that can get to high accuracy, and that there are real proof points of people doing that with open models. I want to touch a little bit on what scaling these agents look like and kind of what I've been tinkering with and thinking about around how an open ecosystem could help with that. And I want to start with the statement of why AI progress, I think, is compute bound. I think it really is limited by compute. I also think it's limited by really good data where you can steer your application anywhere you want to take it. But essentially, at least in the large foundation model labs, more compute has led to better models. And so that is really the thing they are focused on and pouring money into, very, very openly pouring money into. And clearly, it hasn't really fully hit a wall, and I'll tell you why. I know there are articles saying maybe it's hit a wall, but I don't think it's hit a wall based on the original kind of estimate of where things are going. So scaling up parameters has worked. Maybe there's different ways of scaling it up, like with mixture of experts. More training data has helped. Again, that can be synthetic data. I think there was a little bit of murmurs around, are we running out of data? But I think with synthetic data, we're not. And then, of course, more compute, being able to run more data into it at a time so that we can get a model out sooner. And all three must scale together. So bigger models obviously require much more compute to make that happen. to get performance gains, you need more flops. Inference also, I think with all these multi-agent systems, I'm really excited about how much people are hitting these model checkpoints without needing to train them, but that also is very compute intensive. I think there's excitement around, using tools through the MCP layer, model context protocol layer, and that some of those tools are CPU based. So there's kind of this excitement of maybe the fabric between GPU and CPU compute will be much more closely tied and coupled than before. And of course, so far, compute scaling is the hammer that has worked. And this comes from scaling laws. So I don't know how familiar folks are with scaling laws, but it was a very early paper and set of papers back in the day before ChatGPT, so it's a fossil, but it has been pretty much holding. And I think what people don't fully realize is that, it's not like you put in 10x more compute and you get a 10x better model necessarily. It is correlated directionally that way, but it's not necessarily linear. It's actually sublinear. So when people are like, oh, are we tapering out? Are we seeing marginal diminishing? Are we seeing diminishing returns? Actually, this is expected. This is what we expected all along from these models. But what is exciting is that if there are ways to optimize how we leverage that compute, so 10x cheaper compute, that means you can get 10x larger model for the same cost. That's really exciting. Or you can get 10x larger model means you can get to the next order of intelligence, whether that's only a little bit of improvement here, or based on emergent abilities, you can get new capabilities unlocked in a way that you weren't expecting, like a more step function improvement. That's where that's where a scaling laws really kind of clicks in and plays in. So something I've been thinking about is how do we actually get AI to scale in a way that still follows scaling laws, but makes it more available to more people to be able to kind of access the next click of intelligence. So here are some stats, but they're pretty wild. I was thinking about at large, like not even going through the stats one by one, but just at large, just thinking about, have we poured more, crazy amounts of money into orders of more money into people? Yes, these labs have now paid people way more, but I can tell you for a fact my salary has not gone up 300,000x. I wish. No, just kidding. So, well, not really, but like this, maybe for Sam. But this is how much more we are spending, or how much more compute we demand, and clearly that's far more than human capital costs have scaled, right? So this is really where people are putting their money, and they're really focused on making this happen. But it's super not easy, actually. Like, it's not easy to get the model to continue running for a month on tens of thousands of GPUs, hundreds of thousands of GPUs, and not have like a ton of those GPUs fail. If you read the Llama 3.1 paper, it's just like a crazy number of failures throughout the whole training process. So it's so interesting to just understand, okay, well, to get it to scale, we hit up on these other limits at every layer of the stack. So I really think democratizing AI compute will lead to more AI progress, and being able to invite more people to work on this problem will also push AI progress to the limit. And there are many layers of the stack. I'll go through them a little bit quickly, so there's room for questions. But essentially, there's agents that we talked about that you're familiar with. There's hosted services, which you're probably really familiar with, just hitting OpenAI. The models, which we know and love. Inference engines, I don't know how familiar folks are with that, but I can touch on that real quick. Training and development kits like PyTorch, and then GPU programming like Triton or CUDA or ROCm. Of course, the GPU. So agents, you're probably very familiar. So many great things out there today. Guess I should call out Databricks as Mosaic AI agents, but lots of great agentic frameworks there. I'm sure I'm missing a bunch that are built by many of you in the audience, and I hope we'll make it to the top of this slide. Hosted services, also you're probably familiar. This is just hitting your favorite model or your best friend. I think 3 people have independently texted me that Claude is their best friend, which made me realize that the movie Her is happening, at least in the friendship zone. So that's where hosted services are, obviously, maybe not obviously, but it costs money, right? There's not an open source kind of alternative because compute costs a lot of money to scale that out and to maintain it across so many GPUs. The models that we know and love. So different kind of statuses of open, but there are open, fully open source kind of methods, data model, as well as just open weight models out there that we leverage. And I think this is just really a mix out there today and will continue to be. Inference engines I find really interesting. So this is kind of stuff under the model. So how do you make the model move like really efficiently and fast and be low latency for you and leverage your compute that you spent so much money on, that 300,000x on, but you spent so much money on to the max, right? To the biggest possible model or to the most tokens that you can squeeze out of it. And so that's what these are for and what they're focused on. And there's a lot in the open community kind of building these out to be better and writing out different optimizations to improve them. And then training and development, I'm sure many of you spend some time here. I spent my entire PhD here with PyTorch, so I spent a lot of time kind of building out the model architecture, or even doing things kind of at the boundary to make sure that the model runs smoothly, or changing up the architecture of the model slightly, right? Changing it to MoE, LoRa adapters, etc. And then finally, at the lowest layer, just kind of interesting, movement in GPU programming. I think, Triton as a library from OpenAI is really interesting. It can compile down to ROCm and CUDA, so it can operate on both types of chips. And it's an open source framework in Python, so I can write kernels much more immediately. So that's pretty cool as well. So I think things are evolving really quickly. As you can see, different layers of the stack are different levels of open, and there's so many layers. Actually, before really diving into what the layers were, I didn't even realize how many layers there were, and even figuring out the layers with my team took a really, really long time for us to kind of sift through which layer is which, who is what, because there's overlap across them. But openness is rising, and I feel like that's really important for the community to contribute to improving these different layers. But also it is still, I guess there's still barriers, right? So there's still things that remain limited, and I hope to help work on some of that through education and teaching moving forward. So if you want to help or work on that together, I'm super happy to chat. Okay, thank you very much.